Welcome you all once again in this lecture number 6 on metric spaces. In the previous lectures, we have seen the idea of the distance, different kind of the matrices, the diameter of a set, and the boundedness of a metric space or the boundedness of a subset of a metric space. And of course, the diameter of a set always depends on the metric on X. Now, today we will discuss the open sets and the interior points. Okay. So, as you have seen in the course of reanalysis, the open sets are nothing but are open intervals. So, there you define open intervals and then you define the interior point. Okay. But here is again we define the open set and the interior point of a set. Now, this is you can treat as one of the motivations to study the metric spaces. That is to say, how we can define an open ball or an open set or an open sphere in a non-empty set. For example, if you have a set of sequences, what can you think? How would be the open ball in this set? Open ball means, say for example, if we are considering the space plane R2 with the usual metric, okay, then the open ball is the circle, okay, and open sphere is the circle in R2. If you consider R3 with respect to the usual metric, okay, then it is nothing but it is equal to, it is a ball, and that's why sometimes we call it as a ball or it's a sphere. If we are considering the open, if we are considering the usual metric. Now, as we have seen that even in R2, in R3, in Rn, we can define many different kind of the matrices. So, what would be the form? It would be always like the circle or like the ball or something. Or suppose if you have a space, if you have a set of all sequences of or all bonded sequences of real or complex numbers, or if you have a space of all continuous real valued continuous functions defined on a closed interval AB. So, what would be the shape of a ball or of a sphere, open ball or open sphere in this space? So, for that we first give a formal definition of an open sphere or open ball or a closed sphere or a closed ball in an arbitrary metric space. Keep in mind this open ball, because here is everything is depending with respect to the metric. So, what kind of the metric you are considering? It is the shape of the ball or the set will depend on the metric. So, this is you keep in mind. So, let us take suppose you have XD, okay, is a metric space. X naught is any point in X and R is your any real number. Okay, then the set, okay, the set consisting the point Y in X such that the distance between the X naught given point X naught and Y is strictly less than R. Okay, so if the distance is strictly less than R, so take all the points. This set is called the open sphere or open ball with center at X naught and radius R, and it is denoted by SRX naught. SRX naught means the open sphere or open ball with center at X naught and radius R. which is equal to the set of all points y such that the distance between x naught, between the center and the point y, is strictly less than r. And we write in this way. Here we put this bracket, we put the big bracket, the SR x naught, then, and we are taking this is the set of all points y in x such that the distance between x naught and y is less than or equal to r. Here is strictly less than r, here is less than or equal to r. Okay, then this is called, this set is called closed ball or closed sphere with center at x naught and radius r. Okay, so these are the two definitions of open spheres or open ball and closed sphere and closed ball. Okay, now let us say here is I gave an example. Okay, before giving the example, let us have some remark related to the closed sphere or closed ball. Okay, later I will show you what would be the shape of this one. So the open ball and open and closed spheres are always non-empty. These sets are always non-empty. Why these sets? Because you can always test d x naught is equal to 0, which is less than r, whatever is your r. Similarly, d x naught, okay. So if y is equal to x naught, then this is equal to 0, which is less than or equal to r. So it means that the y, you can always, the center always lie is in the open ball as well as in the closed ball. So they are always non-empty, as x naught at the center always lies in the open ball, and open ball is always a subset of the closed ball. You can see here is because here is all the points y such that this is less than r and here is less than or equal to r. So naturally you can see that this is a subset of this set. So here we get this one. And the second remark is that every open sphere in R with respect to the usual metric, every open sphere in R with respect to the usual metric is an open interval. Okay, but the converse is not true. That is, you see that minus infinity to infinity, this is an open interval in R, but it is not an open sphere. Okay, so keep in mind, every open sphere in R with usual metric is an open interval, but the converse is not true. Similarly, every closed sphere in R with the usual metric is a closed interval, but again the converse is not true. Second, the next remark is that for any x, y in the metric space X and R, any real number, R is greater than 0, we have, if X lies in an open sphere with center at y and radius r, this means what? It means that the distance between x and y is strictly less than r, is strictly less than, and this you can treat as y in SRX. Again, because from here we are getting this one, and then again from here we will get this one. So if x, so we have that if x is an open sphere with center at y and radius r, then y lies, if and only if y lies in an open sphere with center at x and radius r. So this is a very important remark that you can. Now let us take some exercises. As I am mentioning from the very beginning, whenever we look for an example in mathematics, you must try first the real line. Check whether the real line satisfying that property or not. So, the first example here we consider the metric space R with the usual metric, and then we will see that the set as the open sphere with center at x0 and radius r is equal to this set. How we will get this one? Look here, I can show you that we write like as r x0, it is equal to set of all points y in R such that we are considering, keep in mind, the usual metric space. The usual metric space means the d x0 y, which is equal to mod of x0 minus y, is strictly less than R. But this is what? This is the same as all the points y in R such that this means that what? This means that you can see that minus R is greater than x0 minus y is less than R. Okay, which means that you can take here is you can add here is this is same as y in R such that x0 minus R is less than we can write like this, minus plus, so we can take minus on the other side and we can take it plus here is, so this would be equal to 1 minute, let us remove this one. So directly we can write this is equal to set of all points, or better is I write in this way that this is minus and here you can write plus, no problem. So it is in R such that this is your minus R is less than minus x0 plus y is less than R. And this means what? This means that it is the set of all points x0 minus R and x0 plus R. So you will get this point. And if you here you have a less than or equal to, then you will have here is like this one. Okay, so this way you can define, you can calculate, you can see that the open ball in the usual metric space is the closed interval, and the closed ball with center at x0 and radius r is the closed interval, this one. Okay. So basically what is we are doing here is we are doing that if suppose here is you have real line, here you have your x0, okay, whatever is your this is your x0, whatever is your r is greater than 0. So here is your you have x plus x0 plus r, and here you have x0 minus r. Okay, and you consider the open interval. This is your open interval. This is your ball with radius r and center at x0. And the closed interval, if you take the closed interval, this one, then this is the closed ball as r x0. Okay, so this way you can calculate. Similarly, we can define the open sphere, okay, or open ball with center at z0 and radius r and closed interval at z0 is in the usual metric space C of complex numbers. Okay, then they are all circular disk of this form that mod of z minus z0 is less than r, or here is less than or equal to r. Okay, keep in mind z0 is a complex number and z is also complex number. Now, again in the metric space, always the discrete metric has some importance, especially in the examples. So suppose X is your non-empty set with the discrete metric D. So here we are considering the metric D is our discrete metric. Okay, then the open ball in the discrete metric is the open ball with center at x0 and radius r in the discrete metric or with respect to the discrete metric, it consists the singleton set. If this radius r, okay, is less than or equal to 1. Okay, this is less than or equal to 1. And it is equal to the whole space if it is r is greater than 1. How can you say that? You can see that by the definition as r x naught is equal to set of all points y in x such that dx naught y is less than r. Okay, but keep in mind because we are considering the discrete metric, so this can be equal to 0 or 1. Okay, so if r is 1, okay, or r is so if r is 1, so if it is equal to, because if it is x naught y naught are different, then it is equal to 1. So 1 cannot be less than 1, strictly less than 1. So if this r is less than or equal to 1, okay, if this r is less than or equal to 1, then this is only, this would be what? This would be equal to 0. So this would be equal to 0 only when y is equal to x naught. Otherwise this cannot be, because r is lies between 0 and 1. So here is you will get this is equal to your x naught. Otherwise you will get when r is greater than equal to r is strictly greater than 1, then this would be a whole space. So this way you can see that the shape of a open sphere with center at x0 and radius r in the discrete metric space, which is equal to x0 when r lies between 0 and 1 and the whole space when r is greater. Similarly, the closed sphere with center at x0 and radius r, it is equal to the singleton set if this r, okay, here is greater than 0 and less than, strictly less than 1. Here is less than or equal to 1, and it is whole space if r is greater than or equal to 1. So these are these are the open spheres and closed spheres in the discrete metric spaces. Now let's see, here is, suppose I consider this very important, I consider x is equal to this set, the closed interval 0 and open interval 1, okay, this, and now this is a metric space with respect to the usual metric. With respect to the usual metric means dxy is equal to mod of x minus y. So if we are considering dx, we are defining dxy is equal to mod of x minus y, then this is a metric on, then d is a metric on x. Okay, and now what would be the shape of open sphere and closed sphere with center at 0 and radius r? So if we take the center at 0 and radius r, then it is equal to the closed interval 0 to r when r is less than 1, less than or equal to 1, and it is equal to the whole space if r is greater than 1. So this is a whole space if r is greater than 1, and it is equal to the closed interval 0, 1 interval this if r is less than 1. And similarly we can define the closed sphere. The closed sphere is the closed interval 0, 1 if r is strictly less than 1 and the whole space if r is greater than or equal to 1. Keep in mind, here is r is less than or equal to 1 and here is r is strictly less than 1. Here is strictly greater than 1, here is strictly greater than or equal to 1. So these are the ways, and later we will see that how we can define these two open spheres or closed spheres with respect by using the balls in the whole real lines. Okay. So this, but here you can see very fast, no problem. Okay, now let us come back to our main thing, that is R2. So here are, suppose we are considering R2 metric space with different kind of the matrices. Then what would be the shape? Okay, so let us consider the x naught is equal to 0, okay, your origin, and radius is 1. Then we define the open sphere, okay, open sphere. This is the open sphere with center at origin and radius 1, which is equal to set of all points y whose coordinates are y1, y2, such that the mod of x1 minus y1 plus x2 minus y2 is less than 1. But x0, x1 is 0, y and x2 is 0, so it is less than or equal to this one. It means that if you consider this, okay, so with respect to this metric, the open ball with radius 1 and center at origin would be of this ball, like this. Okay, this is the open ball with center at origin and radius 1 with respect to this metric. Okay, with respect to this metric. It is not a circle, keep in mind. Okay, or it is not a ball. Similarly, if you are considering this one, this is what? This is the open ball with center at origin and radius 1. And with respect to the usual metric, here you are considering with respect to the usual metric. So if we consider with respect to the usual metric, you see here is with respect to the usual metric, it is like a disk. So this is like a, you can say this disk. Okay, and now if we consider this metric, the open ball with respect to the max matrix, open ball with center at origin and radius 1 is with respect to the max matrix is equal to this one. Okay, so you see that if we are considering the usual metric, only then we are getting a disk. Otherwise, the shape is quite different in R2. Now, let us see another interesting example. Suppose we are considering a metric space CAB. CAB means space of all real valued continuous functions defined on a closed interval AB with respect to the sup metric. Sup metric means that D infinity Fg is equal to the supremum of mod of f of t minus g of t, and supremum over taking over t is in AB. Okay, let us take f naught is any element in this set and r is any real number. Then this is the open sphere with center at f naught and radius r. Okay, so this is the by the definition of SRX naught. So what is the definition of SRX naught? It is we can write as R f naught is equal to the set of all set of all elements G in C A B, okay, such that the supremum of mod of f naught t minus g t is less than r. Okay, and take the t is in 0 AB. So this is the definition. So by the definition, okay, this is what? This you will see that it is nothing but if you take suppose if I take here is this dotted line. This dotted line is your f naught. Okay, this dotted line is your f naught, and here is, this is your r radius, this is your radius r, then this must be f naught t minus r, and this in the same way, and this one is your f naught t plus r. Okay, and it means that all the continuous functions, okay, all the continuous function g whose graph lies within the shaded band of vertical width 2r. So all the like this g, any continuous function within this shaded band. So that is, so you can see that is the open sphere with center at f naught and radius r. So that is the shape of the open sphere. Okay, so you can, open sphere means that we are not considering this one and this one, except this one. If we are including this one, then it means that that it is the closed ball. So that is the way to, you can see that the shape of an open ball in CAB. Okay, now we okay, so this is the way to check the open ball, closed ball, open sphere and closed sphere. Now we will define the interior of a point. Suppose we are considering this is your a metric space with metric D, okay, and this is your a set A, okay, and the point x, the x is a point in A. Then this point x in A is said to be an interior point of A. This point is called interior point of A if x is the center of some open sphere contained in A. That is to say, if there exists real number r greater than 0 such that SRX lies within A. Okay, so then this point is called the interior point of A. Keep in mind, if x naught is the center of some open sphere, not all open sphere. Okay, if we consider, for example, all open sphere, then I can take the radius is little bit bigger, so I can take like this one. This is the open, this is the radius, but this is not. This ball does not lie in A. But I am not saying all, I am saying some open sphere. Okay, so some open sphere. So here there exists R, okay, so there exists R such that SRX lies within A, okay, and the set of all interior points, set of all interior points of A is called interior of A, and it is noted like interior like this one. Okay, in other words, the interior of A is equal to the set of all point x such that SRX is a subset of A for some r is greater than 0. Okay, now what can you say about, suppose you have a point x is here. What can you say whether this point is an interior point? Can you find any radius, okay, such that the open ball around this lies within any radius? You cannot find. But if you take, say for example, if you have a point just before that one, so whatever is the distance from this point to this boundary point, you can consider the radius less than this distance, and then you can find that this is an open radius. So you can find R whose such that this point is the center of an open sphere contained in A. So this point is, but not this point. Later we will define the boundary point, not now. Okay. So here is then we say that the set of all interior point is called interior of the set A, and it is denoted by interior of A, okay, and which is equal to this set. Now, then the set A is said to be open. The set A is said to be open if each of its point is the center of some open sphere contained entirely in A. In other words, you can say that a set is open if and only if each of its point is the interior point. Okay, in other words, you can say that the set A is open if and only if A is equal to interior of A. In other words, you can say that a set A is open if for each x in A there exists R is greater than 0 such that SRX is a subset of A. So there are many ways you can conclude from the definition of the interior point or the open set. So the open set, a set is said to be open if each of its point is the center of some open sphere contained entirely in A. In other words, a set A is open if and only if each of its point is the interior point of it. In other words, a set A is open if and only if A is equal to interior of A. Now, we define the neighborhood. The neighborhood of, so suppose X is in capital X, okay, and A, so here is, so you consider like this, suppose this is my set X, okay, here we have a point X, so this point X is then X is in capital X, then a set, suppose this set, this is your set A, okay, this is called the neighborhood of A. The A is called a neighborhood of X if there exists an open sphere centered at A, okay, there exists, not all, there exists an open sphere centered at X contained in A, okay, then A is called neighborhood of X. In other words, the set A is called a neighborhood of X if there exists R is greater than 0 such that SRX is a subset of A. In case A is open, then it is called an open neighborhood of X. Okay, so now I stop over here and then we will continue the interior point, open set and the close interval in the next talk. So thank you very much.